So sound is a longitudinal wave where energy is transferred through the vibration of particles. Do you remember how to draw a picture of a sound wave?
Yes.
Yes. Whole bunches of dots, correct? And some of the dots are close together and some of the dots are farther apart. The area where it's closer together, what's that called? Compression. And in the areas where they're farther apart, rarefactions. So, with a sound wave, let's say I've got this sound wave. If I change the frequency, if I make the frequency higher, what would it sound? How would it sound different? A higher pitch. Okay. So if I have this sound wave, and I make the amplitude bigger, how would it sound different? And if you remember that amplitude and energy are related to each other, think about making it louder. You are using more energy in order to make it louder. So amplitude and energy and loudness, they all kind of play a role with each other. Okay, there's certain frequencies humans can hear. What are the frequencies? What's the frequency range for a typical human? 20 to 20,000 hertz. Did anybody get up to 20,000?
No.
Right?
Philip
got to like 22 hertz. Philip Bryant got to like 22 hertz. 22,000 hertz.
Who?
22,000. Philip Bryant?
I really got to 17.
I know. I cut off at 15,000 at this time.
I almost blew the speakers like in my house because I was like trying to, do some physics in there. Because like it's a speaker, but it's like round, but it's got like a hole in it.
Okay.
And then like the stuff comes out.
Yeah.
And like I put a piece of paper over it, and I kept making it louder, and the paper go higher and higher.
That's so fun.
There.
All right, well, we're going to pick it up there today. And the first thing I want to talk about is something called the Doppler effect. Now, the Doppler effect, heads up, is an effect that can happen for any wave. We just talk about it when we talk about sound because you have experienced the Doppler effect when it comes to sound. If you are a science, geeky, nerd kind of person or astronomer kind of person, whenever they talk about things being red shifted or blue shifted, that's a product of the Doppler effect. How we know our universe is expanding at an accelerated rate is because of the measurements that we've done with the Doppler effect. So recognize that the Doppler effect is true for all sound waves. We just happen to talk about it. For all waves, we just happen to talk about it for sound in particular. Yeah.
Is this like the Doppler radar?
It is the Doppler radar, the Doppler weather radar, and we will actually use that as an example later on.
Okay. Right, so it's like an effect that you put on?
It's an effect with a series of waves that are produced. So let's talk about that, okay? Let's figure out what it is. So the Doppler effect occurs when either the object making the sound or the object hearing the sound is moving relative to the other one. So in order for the Doppler effect to occur, one or the other has to be moving. Either you're sitting at a stoplight and the ambulance goes by with its siren going, or the ambulance is sitting there with its siren going and you move past it. So one or the other has to be moving, either the thing producing the sound or the thing listening to the sound. What happens is because things are moving, the object catches up with the waves in front, and then it moves away from the waves behind it, so that it has a higher frequency in front and a lower frequency in back. To give you an understanding of what I mean, I'm going to go to this little app and show you something, just a plane, just sitting there creating, it's got its engines on, okay? So there's just an airplane sitting there. This is the sound wave it produces if it's not moving. Everybody okay with that?
Yeah.
All right, so let's set it into motion a little bit. Same airplane, same engine, same sound wave. It's just that now it's not sitting there, it's also moving. So it's catching up with the sound waves in front of it, and it's moving away from the sound waves behind it. So what you actually hear is something like a high frequency ah to a low frequency ah. So that's what it sounds like. You don't have to take my word for it. We can go to the video.
I like when an airplane takes off, like that kind of thing.
As long as it's moving past you, that's the Doppler effect.
Blood soup.
You hear the change in frequency? Is it a change in loudness? No. Now the car does get louder. The sound does get louder as it approaches me because it's getting closer to me. Is that the Doppler effect? No, the Doppler effect is just when it goes from this side of me to that side of me, and it's that change in frequency. Okay. I can also produce it for reals here in the classroom. Physics is so awesome. I tell, I show, I simulate, I do. All right, so we have a noisemaker. And what I'm going to do is I'm going to spin it around so that sometimes it's coming towards you and sometimes it's going away from you. So hopefully you'll hear a higher frequency when it comes towards you, and hopefully you'll hear a lower frequency when it goes away. Is that your experience? Yes, no, maybe?
I feel like I'm in a horror movie. Physics, classroom of horror.
Okay. If we have the Doppler effect going, what? We get something called a sonic boom. This happens when the actual sound wave, the object emitting the sound wave, travels faster than the wave it's emitting. What happens is those sound waves get bunched up on top of each other, and so you have sound on top of sound, on top of sound, on top of sound, on top of sound. They all add together cumulatively, and all of that energy hits you all at once, and that's what we hear as this sonic boom. So, if you have an airplane that's traveling faster than the speed of sound, it's going to have a sonic boom that trails behind that airplane.
Oh, didn't they have like the Concordia or something that went to London?
The Concorde?
Yes.
And it was really expensive, and then there was this accident, and they decommissioned it, so we don't have a commercial airline anymore that goes the speed of sound, but...
It was like 2 hours or something.
Yeah, it was crazy fast. Fighter jets, though, can go faster than the speed of sound, but they're restricted. They can only go over the speed of sound when they're out on the ocean, or if there's like deserted desert area somewhere. Otherwise, they can't. Okay, so that sonic boom sometimes is also called a shock wave. Let's go back to that same applet. And I want you to note that there's this green arrow that's representing how fast my plane is going, and up here it's showing you how fast it's going compared to the speed of sound. Eventually it turns red. So here it's going, there it's going exactly the speed of sound. And so these all get stacked up on one another. I'm going to make it go much faster and watch what happens. Those of you that go boating, does this look like a boat wave to you? So your boat is traveling faster than the water waves it's producing. And so it's producing this wave pattern. A sonic boom is when we're talking about sound, right? So, and what's really interesting is the faster it goes, the narrower the cone. If it goes just the speed of sound, the cone is really fat and wide. And it goes much faster when the cone is really narrow. It's an observation. What's also interesting is you don't hear the sound wave until it hits you. So I'm standing here, I hear nothing, I hear nothing, I hear nothing. Boom! Oh! That plane was way the heck over there by the time I even knew anything was happening. I don't hear anything until the sound wave hits me. Boom! Oh! It's really pretty cool. And let's go to the video and watch that. So you don't hear anything until the boom hits.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft, pushing its way near Mach 1, speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools, and as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. This is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit adweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for adweb.com. Thanks for watching.
All right. So you may have already in your lifetime produced a sonic boom. There's a medieval weapon out there that Indiana Jones particularly likes. Oh, a whip. The crack of the whip, not just kind of swinging it around, right? You can get the tip of a whip, if you know how to do it right, to go faster than the speed of sound. And when you get the crack, that's a little mini sonic boom. So most of you probably don't have whips, but you might have used a belt. A belt.
I had a whip.
Did you have a whip?
I had dressed up as Indiana Jones one year.
Did you?
I don't think my mom took it away.
Sometimes you can get a wet towel to do it. Yeah, yeah. But not all of them are sonic booms. Some of them are just, cracks, but, you can get those.
Those apples on it.
So when we have waves stacked on top of one another, it's a physics term that we call superposition. Superposition can be really exciting, like this sonic boom, but it also can be much more mundane. So superposition is when you have a combination of more than one wave. What's really, really spectacular is that waves will cross through each other. They'll go through superposition, and then they'll uncross from each other and move along on their merry way as if nothing had happened at all. And it happens all the time. When they undergo superposition, what you do is they combine together mathematically with their amplitudes. So if they have two crests, if you have a crest on one and a crest on the other, they will combine to make a larger amplitude simply by adding the two individual amplitudes. That's one way. Or a trough and a trough, you would combine them and they'd make a deeper trough. Or if you have them on opposite sides of equilibrium, if one of the waves has a crest and the other one has a trough, you literally subtract their amplitudes. When they cross through each other, they'll make a smaller combined wave. These are called constructive interferences and destructive interferences. Now I want to show you a simulation. So here I have a right moving pulse and a left moving pulse. I can change the amplitudes, I can change the widths, and I can change whether they're troughs or peaks. So right now they look like this, and I can pause, and I can step it, make it, slow it down. So let's see what happens without me doing anything other than just watching it happen. So they're going to cross through each other, superposition, and then they go back to what they were doing, as if nothing happened at all. So this one is like a 3, this one is like a 2, so when they cross, what amplitude will they have when they're under superposition? It's as easy as that. Don't make it any harder than that.
Is that what happened with the Slinky?
With the what?
The Slinky?
The slinky?
Yeah.
We haven't done that yet. I'll show one to you though. So let's make one a peak and one a trough. So we're going to have a 3 up here meeting a 2 down there. So when they cross,
Wormhole. Oh,
Look at that.
if they're the same, is it a wormhole?
That was crazy.
so there's a 1, right? So could one wave completely cancel the other one?
Yes.
Wormhole. One's 2 and the other's 2.
Alright, so we're going to make this amplitude 1.5 and this amplitude 1.5. The width also matters. If you want to completely cancel them, they also have to have the same width. So I'm going to make them both 2.5 in width.
They're gonna go away.
Oh,
Oh, that was so cool. That was
Watch it one more time, like this, and then let's do it where we pause it and we watch it in slow-mo. So there's going to be some point, I think, right here that doesn't move at all. And right here.
Yeah, that's so cool.
So that special case is called complete destructive interference. Right here. If they completely cancel each other out. Again, superposition happens for all kinds of waves. It can happen for sound waves. So, theoretically, we could have two sound waves that undergo complete destructive interference so that you hear no sound at all. You could take two sounds, and make no sound at all. Let me say that again. You can take two sounds, as long as they are the same amplitude, same frequency, so same width, right? Same amplitude, same frequency, but inverses of each other, where one has a compression, the other has a rarefaction. Play them at the same time, on top of each other, you hear nothing. Yeah.
So like, how does it work with a longitudinal wave?
So with a longitudinal wave, this is the sound wave, right?
Yeah.
So your areas of compression and your areas of rarefaction. They balance, they cancel each other out, is how that works. So let's watch a video and then talk about where you have actually experienced this phenomenon.
No.
Yeah.
The expression, "you can't unring a bell," means that once something has been done, it's impossible for it to be undone. But that word impossible, it's not one we like. The Calais Raw Bell plays the central role in the life of the local people. When it's rung, its sound can be heard across the surrounding neighborhood. In this experiment, GE engineers will be using sensitive acoustic equipment to cancel out the sound of the bell. We'll be using technology similar to that used in our subsea acoustic leak detector. This device carries special sensors that can pick up sound wave vibrations in the water and identify potential leaks. But today, we'll be putting this technology to a very different use. We're going to measure the acoustic properties of the bell, then produce a sound with the same amplitude but an inverted phase. We'll play this inverted phase through these speakers. The two sounds should cancel each other out to create a quiet zone. This process is called destructive interference. We'll place a sleeping baby in this quiet zone. People outside the zone will hear the bell, but if the experiment works, the baby won't be disturbed.
So who thinks they know where you have experienced sound undergoing destructive interference? Guarantee you have.
The tunnel.
In fact, you probably have this technology in your backpack right now.
Headphones.
What's special about headphones these days?
Noise.
Noise cancellation headphones.
Oh, like on your phone when you're talking with them?
Yes. You know what, guys? They actually have a little microphone. They pick up the ambient noise around you. They invert the signal and they play that sound into your headphones so that it cancels out the ambient noise that you're hearing, and your Imagine Dragons song is uninterrupted.
So I can just, when my mom gets denied because I don't hear her yelling at me, it's so
It's
fun.
physics. It is. Noise cancellation headphones. I saw the coolest gadget the other day. It's not commercially available, at least I don't think so, where people that live like in urban areas where it's really noisy, street voices and everything, there was this gizmo that they actually attached to a window that would hear the ambient noise with hitting the window and would convert it and invert it and play that tone to cancel out the outside noise. I thought that was spectacular to make their living environment quiet. So. All right, so that's that technology. Which leads us to something called a standing wave. So this is a progression that we're going through, right? So with a standing wave, we have two waves, and they have to be identical, and they have to be moving in opposite directions. So it's really specific. So that sometimes you'll have a crest meeting a crest, and you'll have constructive interference. And sometimes you'll have a crest meeting a trough, and you'll have complete destructive interference. And then you'll have a trough meeting a trough, and you'll have complete constructive interference. And this happens over and over and over and over again, so that what it looks like is one wave that doesn't look like it's moving right or left. It looks like it's standing still, and why we call it a standing wave. Standing wave is produced when you have two identical waves traveling in opposite directions. They undergo constructive interference, then complete destructive interference, and then constructive interference, and then complete destructive interference, over and over again, so that it produces what looks like one wave standing still, not moving to the right or moving to the left. This is the kind of wave that we get on, like, stringed instruments, for instance. We want to go ahead and demonstrate this for you in a couple of ways. We're going to do it with the slinky, and we're going to do it with our pink vibrating string. There's a couple of places of note when we have a standing wave. There's areas that don't move at all, and those are called nodes. And then there's areas that move maximum to maximum, and those are called antinodes. So as I do the demonstration, we'll look for those specifically. So let's go ahead, we're going to do the Slinky O Science in the back. And I literally need everything moved out from underneath that table. And I need for you guys maybe to sit up on the counter. And I need one volunteer. Okay, I need this entire zone completely empty. And you can sit up on you will want to sit. You will want some counter or sit on this desk so you can move down on this process. Who wants to be my partner?
You hit that.
Link you
Well.
Okay.
The other way.
So when I produce a wave, it travels from me to Raven, and then it reflects back from Raven to me. Do you see that? So that's how I'm going to get two identical waves going in opposite directions. I'm going to have a wave that I produce, and then the wave that gets reflected is the second wave. Now, I have to do this in a way that the reflected wave completely identically matches the wave that I produce. I'll know I've accomplished that when I get a standing wave. And it'll look like one wave that's not moving towards Raven or me. Alright, so that's what we're looking for. Here we go. So that looks like a pretty good standing wave to me. If I'm not right, you see it looks like it moves towards Raven or towards me. Here. You see what I mean by sometimes it looks like it's moving towards Raven and sometimes it doesn't? When it's not moving towards Raven, that's the standing wave. Right there. Okay, let it go. And let's come over here to my pink string science. For the pink string, you will want to be eye level with the pink string. You will want to be eye level with the pink string. The string itself is what's going to. Well, it's weird. The string itself is what's going to be vibrating. Again, I have to wait for my computer to go. And again, I'm going to produce a wave here. It's going to travel through the string. It's going to reflect back on itself. And I have to produce a wave that fits this string perfectly. I need to find a wavelength that's exactly the same, will fit nicely on this string. So I'm going to start with a frequency of 6 hertz. And that's not a standing wave. There we go.
That's so cool.
So this is a standing wave. We have a node on this side and a node on that side, and the antinode is right here in the middle. That's one segment. And that's 7 hertz. I'm going to go up to 14 hertz. So how many nodes do I have now?
3.
3. One on each end and one in the middle. And I have 2 antinodes. Is this one wavelength or 2 wavelengths?
Whole thing?
Mm-hmm.
So,
One wavelength, because a wavelength has a crest and a trough, right? So if this string is 4 meters long, the wavelength that I'm producing is 4 meters. You guys okay with that? So what's 14 plus 7? 21?
I'll be gone. Wait, where are you saying? There's 3.
There's 3 antinodes.
Where's the second?
I want to touch it.
This is an antinode here, this is an antinode there, and that's an antinode there. Okay, so
Oh, the
gradient.
antenna is this one.
No, the node, that's a node. We've got 1, 2, 3, 4 nodes. Okay, so gradient, what you can do is you can pinch right at that node. Don't you do it, he's gonna do it. And so you have then dampened that end over there, right? Which is not affected the wave over there. Alright, so 21 plus 7 is 28. So it looks like a blur, right? It looks, the one on the slinky didn't look so much like a blur. This sure does look like a blur. What's happening is you're getting constructed, destructed, constructed over and over and over again.
I don't know what.
Increase the frequency and make that frequency.
So let's draw one of these in our notes.
No, she did. I was
Oh,
going to she got it.
Hey,
The way that you draw a standing wave, it's nice to use color if you have color available. Is there are times when there's constructive interference. And then there are times when there's complete destructive. And it looks like a straight flat line. And then it flips so that there's constructive interference again. And it happens over and over and over and over again, so it looks like a blur. In the wave that I just drew, how many nodes do we have? 3. How many antinodes? 2. And if the length of this string is 4 meters, the wavelength that I've got on here is 4 meters, right? Because I drew one wave on that wavelength. This is how stringed instruments will vibrate. Because like if it's a violin, one end is attached to the bridge and one end is attached to the fret. That kind of thing. So the ends are fixed. So only something that goes from a node to a node, that's the only frequencies that are allowed on that string. Unless you put a finger somewhere and you're changing the length of the string, which changes the note you're going to be playing on that string.
So the nodes, there's 3 nodes, right?
In this one there is, right? In this one there is. But I showed you on that pink string, I could do lots of different variations. So we're going to conclude today by talking a little bit about timbre. So we've worked our way all the way to something called timbre. I know it doesn't sound like you're supposed, it doesn't look like you're supposed to say it that way, but T-I-M-B-R-E is pronounced timbre.
That's a one name on iPhone. I
How
promise.
is,
Yeah, how is the tambourine spelled?
how is what?
Tambourine.
Tambourine?
T-A-M-B-O-U-R-N-E.
Yeah, O-U-R-N-E, yes.
Should have spelled tambourine.
Tambourine.
So, timbre. Timbre is spectacular. I love timbre. Timbre is a description of why a musical instrument sounds like it does, even if it's playing the same note. So if we have our eyes closed and somebody plays the note C on the piano, and somebody plays the note C on the flute, I guarantee, even though they're both playing the same note C, you could tell the difference between the piano and the flute. So timbre is a description of why a musical instrument sounds the way it does, even though it's playing the same note. Now here's why this happens. What you've got going on with timbre is you've got a fundamental frequency, the note being played, but because of the instrument, because of its shape, its size, the kinds of materials it's made out of, heck, even the rosin, like for a Stradivarius, that makes a difference. You have these other frequencies called harmonics that just kind of ride on top of the note. Doesn't change the note. All it does is it contributes to the quality of that note, so that a piano playing the note C sounds different than a flute playing the note C. So these other harmonics just kind of right on top of that note being played. So let's listen to what I'm talking about with these fundamental frequencies and harmonics. This is going to be a video of a device that measures the frequencies being played, and it displays them in graph form. So there's going to be a note being played, and it'll tell us the instrument up here. And you can see all of the frequencies that are resonating with that note because of its timbre. So it's telling you what note it's playing as far as the frequency goes. So a grand piano, this is the note being played. Notice that it's the widest one, the highest amplitude, but that's not the only frequency that's also being produced. It's the key that was hit, but besides that, you also have these other frequencies that are just riding along the top of that fundamental frequency so that it sounds like a grand piano. We're going to see other things as well, other instruments as well. Timbre. Interesting. There is one musical instrument that plays one frequency and only one frequency. There are no harmonics. Any guesses as to what musical instrument that is? It's kind of a little deceiving calling it a musical instrument. We have them in the classroom right now and you play with them. The tuning forks. They're called tuning forks for a reason. They actually use it to tune to a frequency, right? Printed on the tuning fork is a frequency. That tuning fork has no harmonics. It's the only thing that we drop that does this pure tone for us. So let's go through a couple of conceptual questions. I want you to guys talk to each other first before I call on somebody to answer. So the first two questions, can you explain how noise cancellation headphones use complete destructive interference? And suppose you set up a standing wave of 6 segments, how many wavelengths, how many nodes, and how many antinodes? So talk to each other and then I'll call on somebody using those magic cards.
Yeah, you don't see, you wrote that in my output. Why do you put versus
6, so you have a stamp.
Well, you start standing, it's like, wow.
There will be 12 wavelengths and 12 frequencies.
What are you talking about, Michael? What? Break it down. And point,
So the anti-node is when this one point that goes from maximum to maximum, right? This is only one string, would you agree? But this point right here goes from that maximum down here to that maximum. So this is an anti-node right here. Okay, so Gabby, Fire Covenant, tell us about noise cancellation headphones.
So, the way you sort of explained it was that there's a little microphone within your headphones, and it picks up the ambient noise, and it matches the frequency so that it cancels, and you can hear your music clearly without hearing any of the ambient noise outside.
Great. Now, the better quality of technology, the better the noise cancellation technology. The better the noise cancellation. The more you pay for your headphones, the better quality you'll get from that noise cancellation. They're not all created equal. It's
Even
kind of
canceling buds now.
I know.
It's so crazy.
Yeah.
They're like $500 for like little itty bitty ones.
Wait, what's number 2 say?
Inverts the signal and feeds this into your headphones.
Feeds it.
Feeds this into your headphones. It feeds the inverted signal. Lays it on top of the music that's going into your ear.
That's why when I only play them, like open them low and without playing any music, you can also hear the noise
Right.
going on.
Right. Okay, let's go to the standing wave of 6 segments. How many wavelengths do we have? Liliana Vess, Anna. How many? 1. No, there's much more than 1 wavelength. Because 1 wave would be right here. How many wavelengths on this? 3. There's 1 wavelength, here's 2 wavelengths, here's 3 wavelengths.
Wait, but you count the others or no?
It's 1 string. It's just this is that string, what it looks like at different moments in time. This is not 3 strings, right? There's just 1 pink string back there. It just looks like a chord, right? Okay, how many nodes do we have? Dynacharge, Alana. 7. 1, 2, 3, 4, 5, 6, 7.
I thought I was hallucinating whenever I counted 7. I was like, no, I can't do it.
And how many antinodes? Essence Backlash, Celia.
Would there also be 7?
They're not 7 antinodes. Ethan, Guardian Lions, how many antinodes? 6. 1, 2, 3, 4, 5, 6. What wavelengths can fit onto a 1 meter long string? Any ideas?
0.5 meters?
Infinite.
0.5 meters. If we had 0.5 meters, then one wave would fit right here. And we'd have 2 waves. Right? If the whole string is 1 meter, we have wavelength of half a meter, well then the whole entire wave would fit on half of the string. Can you give me another wavelength that'll fit on a 1 meter long string? 1 meter.
Good point. 0.5 on.
Good point.
Yeah, well,
0.9 meters will not fit on this string because we need to go from a node to a node. It has to fit perfectly.
0.25?
0.01.
0.25 would.
1
1.1?
over an integer.
Say that again.
1 over an integer.
1 over an integer? No.
No?
No.
1/3 or like so.
Oh, well.
1/3 or 1/4 or 1/5.
Not necessarily.
Did you just take?
1/4.
Would a 2 meter long wave fit on this string?
Yes.
Oh yeah, I would.
You can only get
So could you take any even number? Just kidding.
Could a 3 meter long wave fit on this string?
No.
No, because we have to go from a node to a node, right? That's the rule for a standing wave. And if it's a 3 meter long wave, then your nodes would be at 1 and 1.5 meters.
About 0.3.
What about 0.3?
0.33.
0.33? So then you would have 3 waves in one, yeah, that one would work. As long as it goes from a node to a node, you're good, and that will fit. When experiencing the Doppler effect from a sound moving toward the listener, does the listener encounter an increase in wave frequency, speed, loudness? All 3? None of these? Doppler effect. Does the Doppler effect involve frequency? Yes. This one's a yes. Does the Doppler effect influence the speed of the sound? No. The speed of the sound is the speed of the sound. If the medium, like the air, doesn't change, then the speed of sound is still the speed of sound, whether you're driving a car through it or not. What about the loudness? Does Doppler effect affect loudness? No. The Doppler effect is only involves frequency.
Did 4.0 fit on the...
No, it couldn't.
Okay, so 2 is the highest.
2 is the highest.
Okay.
Because you need to go from a node to a node.
So anything less than half, or
More than
half
2.
would never work.
Correct. Astronomers find that light coming from point A at the edge of the sun, let's say it's this edge, has a slightly higher frequency than light coming from point B at the opposite side. What do these measurements tell us about the sun's motion? Yeah, it's rotating. Yeah. And we actually see that in our spectroscopes. In chemistry, remember looking at the spectrum and those things, right? If the object is moving towards you, that entire spectrum will be shifted towards the blue. If the object's moving away from you, that entire spectrum will be shifted towards the red. and why it's very difficult as an astronomer to look at elements unless you know whether something's moving towards or away from you. This is how we know things are moving towards or away from us, how fast they're moving towards or away from us, and that our universe is accelerating. Is we're really, really, really good at measuring these spectrums and seeing these red shifts and blue shifts. Why do you see the baseball being hit and then hear it hit?
Light waves travel on size for the time.
We already talked about that with E equals MC squared too. One final video today. So what we have here is a metronome here in the front of the line. And they were told to clap when they heard the metronome.
I'll look again. Yeah.
They have their eyes closed so that they're not influenced by the person in front of them.
They're not fall over.
I guess they're good at standing on their feet with their eyes closed.
You should keep your eyes for your equilibrium. I would've-
Apparently these people are.
These are aliens.
Something wrong with them, they can stand more than 2 feet.
All right. So homework tonight is this here.
This is when they like snakes to travel.
Or the travelers for the.
Yeah. But they're not. They're
Good.